My screen okay? I think you guys are still muted, just so you know. There we go.
Yes, we can see your screen.
Thank you.
Yep.
So we finished up the dosage calculations. Everybody should have their tests back. If you don't have your tests back from that, if you're here, come talk to me. I'll give it to you. If you're at New Richmond, send me an email and I will reply with your test attached to it. Those of you at New Richmond, if you're having problems seeing what's marked wrong, if you open it up on a computer at the school, you should be able to see the inking. But if you're using an older version of Microsoft Word, it sometimes does not show up. So that might be the issue. And if you can't get the inking to show up when you look at it at all, let me know and I'll just send you a list of what problems you have wrong so you can go back and look at them. As a group, we did pretty well on the test. I was pretty happy with it. Okay, so today we start the material. These last 5 weeks or so, last 5 lectures, deal with material that are kind of for the next step. If you're in the nursing program, most of you at some point are going to go on for a bachelor's degree, partly because it's pretty much going to be required here. And 2 classes that you'll have to take after you leave the 2-year program is you would need a college algebra class and you're going to need a statistics class. Almost every bachelor's program you go into is going to require those 2 courses. Some of you might be able to test out of a college algebra class, but all of you will have to take a statistics class at some point. So for the next 2 weeks, we're going to be talking about some of the basics of college algebra. By no means are we going to get into the heavy details. We covered some of the very basics in Unit 1 with solving equations and working with algebraic numbers and variables. And we're going to cover a little bit more here with graphing and relationships and stuff like that. And then so 2 weeks from today will be the unit test on algebra. What does that work out to be? May 5th, I believe, will be that unit test. Then statistics is only going to be 1 week of lecture. So we'll lecture on that on May 12th. And unfortunately, the way the calendar is set up this year, our last class is graduation day on May 19th. So on May 19th, all we have planned is that last test on statistics. So if any of you have other plans that day, I will make sure I have that test sent out to New Richmond by Tuesday or Wednesday or so of that week so that it's available for you. Those of you here in Rice Lake, same thing. You can just come in here if you'd like to take that test earlier in the week. Because of the timing on that statistics test, most of you won't have time to redo problems and hand it back in. You won't have time to do corrections on it. So what I'll try to do is I'll just try to write that test easier so that there shouldn't be a huge need for corrections on it. It's against my nature to make this stuff easy, so I'll try as hard as I can, I promise. So anyway, let's go ahead and start talking about the algebra stuff. What we're going to look at today is, rather than looking at single values, we're going to look at relationships between values. And when you start talking about relationships between numbers, you might look at things like height and weight are always a simple one. The taller a person is, the more they tend to weigh in general. So if you have a list of heights in inches, and you have a list of weights, for the most part, in general speaking, generalizing, you can match them up like that. And that's really what the beginning parts of algebra, the very basic level for the graphing consists of, is matching up 2 sets of numbers like this. And we're using one set of numbers as a predictor variable. This is often referred to as an independent variable. And then the other variable is kind of the, I don't want to say resultant, but we'll go with that for now. The resultant variable, often called the dependent variable. The reason it's termed this way is if you know the height, it gives you a little bit of information. You should be able to predict a little bit about their weight. So this is the height changes, the weight is forced to change based on their height. Again, it's not perfect, but you get the idea of the relationship. So what we need to be able to do is graph numbers that have a relationship like this. We can write them out in a list as a single pair, like for example, 68 goes with 162. We can write them out just like that and make what we call an ordered pair. And as long as we know that we're comparing height to weight, this is where the ordered part comes in. We know that the first one represents the height, and the second one represents the weight. So not only do the numbers themselves matter, where they're located within that pair matters. So we need to look at graphing those, representing them graphically. And we have looked a little bit at graphing numbers, representing numbers. Back in the first weeks of the class, we talked about the number line. When we were working with integers, positive and negative numbers, we use the number line to represent a number. For example, if we had like a 4, one way we represented that is to take an arrow from 0 and going to 4. Or if we had -7, we'd take an arrow, we called it a vector, from 0 to -7. Which is a great way of representing it if we're going to calculate with it. It's a good working representation. We can combine those arrows, those vectors, to add and subtract numbers. But if we're just representing values themselves, it's simpler and takes up less space if we just put dots. So we can represent 4 with just a dot at 4, -7 with just a dot at -7. So for representing single numbers, that works really well. But if I needed to represent an ordered pair, for example, let's say I have the ordered pair 3 and 7. And I need to not only represent both values, but I need to represent their order. I mean, I suppose I could put a dot at 3 and a dot at 7 and connect them with a line, but I would have to use an arrow or something to show that one of the 3 comes first and the 7 comes next. But if I'm representing a lot of ordered pairs, that's going to get very cluttered as well. So the solution to this, for representing this, was came up about 2,500 years ago by a man by the name of René Descartes. And what Descartes came up with was, we're going to take this number line and we're going to use one of them just like we always do, with the 0 in the middle, positives going off to the right, negatives going off to the left, just like always. And that's going to be referred to as our independent axis. Some of you may have heard that referred to as the x-axis. And then Descartes took a second number line, but instead of running it horizontally, he ran it vertically. through the 0 of the first number line, and the 0 of the second number line was at that same spot, numbering up as positive and down as negative. So now to represent an ordered pair like 3, 5, of course, I should get ahead of myself. This second axis is called the dependent axis, or many of you may have heard it referred to as the y-axis. So in that ordered pair, the 3 is the x value, or the independent value. That's the predictor value. We're using that value to predict the other value. So that's going to be at 3 right in here. The second value is the dependent value, or the y value. That's the 7. Well, to represent those two numbers together, we basically use a shadow. We go out in the middle of space out here, and we find that point like that. Its shadow falls on 3 on the x-axis and 7 on the y-axis. That point is 3, 7. When we're naming a point, we always name the x value first, or the horizontal value first, and then the vertical value, the y value. So, who can tell me what's the coordinate? What is the ordered pair for that point right there?
6, 2.
6, 2. Very good. How about that one? Yes, -3, -4. Good. And let's see. How about this one?
-6.
4, -6. Wonderful. And how about this one? -4, 5. Good. A little bit trickier is if I give you a point on the axis. What would that one be called? 7, 0. Good. Because it's 7 on the x-axis and its shadow on the y-axis does still fall on 0. Or how about one here? 0. 0, -3. Perfect. Because again, its shadow is at 0 on the x-axis and it's a -3 on the y-axis. So what you'll see is anything that is on the x-axis has a y-coordinate of 0. Anything that's on the y-axis has an x-coordinate of 0. The graph is then divided up into 4 sections. They're called quadrants. This quadrant over here is called the first quadrant, and that makes sense. Both x and y, I'm going to refer to them as x and y instead of independent and dependent, just because it's quicker. Both x and y are positive over here, and so that's usually where most of our data is going to get graphed. So that's the first quadrant that we would use. That's why it's called the first quadrant. From there, it's a little bit arbitrary. What they chose to do is they chose to go around the graph like they do in trigonometry and navigation and stuff like that. So this is called the second quadrant over here. Third quadrant. And then down here is the fourth quadrant. And then, of course, this spot in the middle where the 0 point of both number lines overlaps is referred to as the origin. It's called the origin for a few reasons. It's It's where the axes overlap, but it's also where everything begins. When we start looking at shortcuts for graphing with lines and stuff, everything with our graphs begins at that point. So there's going to be a lot of things that we graph on a graph like this. And as I said, most of the time, we're going to be using simply that first quadrant. You know, we might be looking at time in hours and medication given in milliliters. Now, first of all, you notice I don't have to number every mark on my axis. I originally only numbered the 5 here, but I can go back and number the rest of them if I want to. But just having this one numbered, just like with our syringes, we can always go back and look between the markings and tell, you know, figure out what each marking is worth, assuming that this first marking is 0. Same going up this way. I only have the 100 labeled, but if I assume that this is 0 here, there's 1, 2, 3, 4, 5 spaces between 0 and 100. I can figure out that each of those markings is 20. So they don't all have to be labeled. And a lot of graphs would get pretty cluttered if we did label all of them. As you can see, it looks kind of cluttered with all of those written in there right now. So let's, for this graph, let's say that at time 0, they had not been given any medication. At the end of the first hour, they had been given 30 milliliters. Second hour, they'd been given 60 milliliters. Third hour, they'd been given 90 milliliters. Fourth hour, they've been given 120. So we can see that a straight line goes through those points. And let's say we stop keeping track at that point, or we've reached the 4th hour and we haven't made it to the 5th hour yet. We can use this to predict. I'm going to switch colors so you can see that the next piece is prediction. If I extend that line out, I can predict. At 5 hours, I trace that up until I hit the line. And I trace it over, I can see at 5 hours we would expect that they would have received 150 milliliters of medication. So these graphs can be used to not only track what's going on, but then to predict what's going to happen next. Or we could also predict in the middle here. Let's say we didn't take a reading at 2.5 hours, but we did take a reading at 2 hours and at 3 hours here. We can predict what it would have been or figure out what it would have been at 2.5 hours by tracing that up and over. And we see that that hits at about 75. So at 2.5 hours, it would be at 75 milliliters. Now you can see right here one of the weaknesses of a graph. Well, one, I drew it kind of sloppy and my lines are all crooked, is a major weakness, but even a well-done graph, one of the weaknesses is when I trace this over here and I get this point on the axis, trying to figure out exactly what that number is. I knew because I made up this relationship that that had to be 75. But if I was just tracing this over and trying to figure out what it was, I would know, is that 70? Is it 80? It's hard to get exact numbers. So a graph is not good for trying to figure out exact values. One thing that I will warn you on graphs that does happen, that'll mess you up, messes a lot of people up. What does it mean when they do that on the axis? But look at the numbering. What's happened there? Yeah, we skipped a bunch. That little double slash there, that symbol, is a symbol saying that basically what it means is a piece of the axis has been cut out and removed. So if there's no points that occur below that, they'll a lot of times do that so that you don't have a lot of empty space on the graph. So we might have points that look like this. These graphs do not always have to be a straight line. This one's a curve. Since there was nothing below 520, they chose to cut out that piece that was way down there. Now, one of the unfortunate disadvantages of this is it looks like from here to here that the amount has doubled, and it really hasn't. Because if that part of the axis had not been cut out, bless you. If that part of the axis had not been cut out, this graph would look something like this. There's my spacing's way off, but get the picture. So that shows that really it's only been a slight increase from here to here. It has not doubled like it looks like it did here. The reason they would do this, though, is one, they eliminate all this empty space, and by doing that, now you can see that this is a curve, whereas here, it's really hard to tell, is that a curve or is that a straight line, because everything's so tightly grouped together. Sometimes they'll actually just start numbering at 500 instead of putting in that little break, which is even trickier yet. And then next section, we'll talk about numbers being used to deceive. And I'll show you, how that can be used as a very misleading practice to do things like that as well. Okay, so let's hit the next point. We have solved equations that look like this. 7 equals 3x minus 2. We solved it by doing what was the first thing we had to do? Add to the 2 to both sides. So 7 plus 2 is 9. Over here, the 2 is just gone. So we got 3x. Then what? Divide by 3. So the 3 is gone over here. 9 divided by 3 is 3. So x equals 3. Or 3 equals x. We could also have an equation that looks like this. What steps are we going to take to solve this equation? Same steps. We're going to add 2. 15 equals 3x. And we're going to divide by 3. We get 5 equals x. And we might even have something like this. 22 equals 3x minus 2. The steps to solve it are going to be same thing. Add 2. Divide by 3. These are what we call family of equations. It's the exact same steps to solve every one of them. But each one of them gives us a different value for x. So rather than writing out each individual equation like this, because this family would contain an infinite number of equations, because the family is 3x minus 2 on one side, and then any number I want to put in on the left side. So to express that whole family, we write y equals 3x minus 2. To solve this, we can't solve it with the methods that we have been using because there are two variables in it. So what we have to do for this one, similar to what we did up here, is we just had values put in where the y was and solve for x, is we just pick values. Now, rather than picking values for y and solving for x, it's a lot easier if I pick values for x and solve for y, because I put the value in here for x, all I have to do is order of operations and calculate y, because y equals that other rest of the expression. So what we'll do here is we'll make a table. This is another reason why the x variable is often called the independent variable, and the y variable is called the dependent variable, because of what we're about to do right here. For x, I can pick any value I want to. I'm just going to pick several numbers for x. So I might pick -3, -1, 2, and 5. The values of x are independent. I can pick any numbers I want to. Now in a minute I'll come back and I'll explain why I picked those values. But now let's figure out what y has to be. If x is -3, y has to be 3 times x, 3 times -3, minus 2. So what's 3 times -3? -9. What's -9 minus 2? -11. So that gives us the ordered pair -3, -11. X is -3, y is -11. So you can see here, I was able to pick whatever value I wanted to for x. Once I had x, then we found the value of y. The value of y depended on the value of x. That's why y is the dependent variable. If x is -1, y has to be 3 times -1 minus 2. What is 3 times -1? -3. What's -3 minus 2? -5. So when x is -1, y is -5. Gives us an ordered pair. When x is 2, y has to be 3 times 2 minus 2. What is 3 times 2? 6. And 6 minus 2 is 4. So that's telling us that when x is 2, y is 4. Giving us another ordered pair. And finally, if x is 5, y is 3 times 5 minus 2. What's 3 times 5? 15. And 15 minus 2 is 13. So that gives us that when x is 5, y is 13 for another ordered pair. Well, how many of these ordered pairs could I make? As many as I wanted to, right? There's an infinite number of them I could make. So I can't possibly list out all of them. But each one of them is a solution to this equation. If I put them in, if I put -3 in for x, I will get -11 for y. So the way I represent those solutions is I now come back to this graph. Now you'll notice I made the spacing a little tighter on the vertical axis than I did the horizontal. That's just fine. You don't have to have the same scale on each axis as long as it's consistent within that axis. So now I can plot these points. -3, -11. X is -3. Y is -11. It'll be down here. Got to go another point yet. I have x is -1 when y is -5 is right there. X is 2 when y is 4. X is 5 when y is 13. And if I had done my graph well here, you see that comes out to be a straight line. what does that line represent? Well, that line represents every possible solution to this equation. Now you'll notice I put arrows on the end of that line because that line keeps going. I can go straight out in either direction for as far as I want to go, and I will keep finding solutions to that. You know, we did not use 3 for x, but if I go here to 3 and I trace it up to my line and I trace it over here, I get the y is 7, and that is a solution. When x is 3, y is 7. You know, just like we were tracing on the graph before, every point on this line is a solution. I might have a point here at -1.5. Well, at -1.5, this should be at negative, well, it should be over here. -6.5 is where it should be. So my line isn't real straight. You guys get the picture. Every point on that line, I can find its x-coordinate and y-coordinate, and it should be a solution to that equation. Now, not all equations are going to form lines. The reason why I chose these points, now the specific values are just random. I just picked them. But I wanted to choose points that were scattered across the x-axis. You can see I have -3, -1, 2, and 5. What that does is that's going to give me points that are scattered across the graph so that I can kind of connect those points to figure out what shape it is. I didn't know when I picked these points if they were going to be adequate to figure out what shape my graph was. In this case, I knew it was a line, so I guess I did know it was going to be enough. All I need is 3 points to define a line. I never know for sure when I'm picking those points if it's going to define it. So I just pick some, I try them, and I may have to pick more later. For example, let's look at one that's a little bit more complex to graph. Let's do y equals x squared plus 2x minus 15. So once again, I just need to pick values for x. And then we're going to figure out what the y values have to be. So I'm going to go with like, well, let's do -3, -1, +1, and we'll do +3. And notice I gave myself a little more room here because it's going to take a little more room to figure these out, figure out the y values from it. So if x is -3, y is found by putting -3 in for x. So x squared becomes -3 squared, plus 2 times x becomes 2 times -3, minus 15. Now, again, be very careful when you put this in your calculator because a negative number squared better be positive. So -3 squared is a positive 9. 2 times a -3 is a -6, minus 15. 9 plus -6 is 3. 3 minus 15 is a -12. So I get an ordered pair when x is -3, y is -12. So -3, -12 is somewhere down there. I could just punch that into my calculator, but again, I have to be careful. I do parentheses, -3, close the parentheses, squared, plus 2 times -3 minus 15. And I get the -12. If x is -1, y is -1 squared plus 2 times negative 1 minus 15. Negative 1 squared is 1. 2 times negative 1, negative 2 minus 15. 1 plus negative 2 is negative 1. Minus 15 is negative 16. So that gives me the point negative 1, negative 16. So I've got negative 1, negative 16 is right down here. Any questions so far? So if x is positive 1, y is going to be 1 squared plus 2 times 1 minus 15. What is 1 squared? 1. Good. 2 times 1 is 2 minus 15. 1 plus 2 is 3. And 3 minus 15 is negative 12. So we get the ordered pair 1, negative 12. So this is obviously not going to be a straight line. So let's use x equals 3 now. So it's going to be 3 squared plus 2 times 3 minus 15. What's 3 squared? 9. 2 times 3? 6. I still got minus 15. 9 plus 6 is 15, and 15 minus 15 is 0. So that gives us the point 3 comma 0. So right there. So now at this point, I've used up all the points that I chose. I'm going to need some more because I really don't know exactly how to sketch out the graph yet. It looks like it's going to go something like this. But it looks like maybe I need to know more over here yet, so I might use like negative 4 or negative 5 over here. And maybe I should try like 0 or negative 2 or something here to see what's going on. Do you see how I came up with those points? I'm just looking at the graph. I want to know what happens here, so that'd be at x equals negative 5. And I want to know more about what happens in here. Wouldn't hurt to use 2 here and figure out what's going on in there too. But let's start out using negative 5 and see what happens with that. So if x is negative 5, y is going to be negative 5 squared plus 2 times negative 5 minus 15, or yeah, minus 15. Negative 5 squared is 25. 2 times negative 5, negative 10, and then minus 15. 25 plus negative 10 is 15. And 15 minus 15 is 0. So we've got negative 5 comma 0. Puts us right here. Let's use x equals 0 just to see what's going on there. I like to use 0 for an x value because it's usually relatively easy to figure out. So that's 0 squared plus 2 times 0 minus 15. Well, 0 squared is 0. 2 times 0, 0. So we've got 0 minus 15 is just going to be a negative 15. So our ordered pair here is 0, negative 15. So that's right in here. For the sake of time, I'm going to give, if I put in negative 2 for x, I would also get negative 15. So I get a point right there. So what we're getting here is kind of a U-shaped, it's called a parabola. You get a parabola anytime We talked a little bit about degree of algebraic expressions back in week 2 or 3. This formula here for y has a degree of 2. It's got an x squared in it, is the highest power on the x. Because of that, it's going to form a parabola. And for now, for this class, to graph a parabola, we're going to make tables like this and plot those points. And it takes a while to get good at picking out what points to use to put them on the graph. So for the next 9 minutes or so up until break, what I'm going to have you guys work on is I'm going to put a worksheet up here that has different graphs on it. And I want you guys to complete the table and graph the equation. So I'm going to put these 4 up there for now. In about 5 minutes or so, I'll scroll down to the next 4. Can you guys see those? Or those two? Oh, the equation there. Are those big enough that you guys can read them, or do I need to blow them up?
Can you blow them up a little more, please?
Sure. Let's see if I can still get them all on the page here.
I can see them.
There we go. Now, you can see I suggested numbers here for you. I just suggested numbers to use for x. You don't have to use those if you don't want to. You don't have to use all of them. You don't have to use any of them. You can use your own. I just put suggested numbers in there to help you get started on them. Okay, it's time for breaks. What I'm going to do is I'm going to have you write down the equations for these two quick, for 3 and 4. And I'll scroll down to the next ones, and then we'll go ahead and take our break. So 3 is y equals x squared plus 2x plus 1. 4 is y equals the square root of x plus 6. Then those will be the next 4 after that. So I'll go ahead and we'll take our break, come back around 9:30, and you want to start back in on these, and we'll discuss them in a little bit after that. If you don't get them all done, it's not a big deal. I just want you to get a little practice with them before I show you what the graphs look like.